In this video, we are going to look at what happens if one of A, B, or C equals 0 in the standard form of a quadratic equation. We obviously can't have A equals 0. That would eliminate the quadratic term and leave us with only a linear function. So specifically, we're going to focus on what if C equals 0 and what if B equals 0. So in our first example, we have the function f of x equals negative 2x squared minus 6x. In this case, we're going to have a equal to negative 2, b equal to negative 6, and our c is going to be 0. The fact that c is 0 has no bearing on our vertex. Remember, our formula for the vertex is the opposite of b over 2a. So that's the opposite of negative 6 over 2 times negative 2, which simplifies to be negative 1.5. So our axis of symmetry / our vertex is going to be on the line x is equal to negative 1.5. So we know this is going to be our symmetry axis. Using negative 1.5 in the function, and you can check my arithmetic on this if you want, but it's not a good use of our time to go through all of the individual calculations. Evaluating that expression, we get that the value of the function at x is equal to negative 1/2 is 4.5, which means we should anticipate a vertex at the point negative 1/2, 4.5, which is right there, right on top of our axis of symmetry. And that's going to be the point negative 1/2, 4.5. Now, I failed to mention at the beginning, we should have clocked that a was negative, meaning our parabola is going to open down. So I'm comfortable writing this point up above it, as I know the rest of the parabola is going to be opening down. The fact that the parabola is going to be opening down, but the vertex is above the axis, means that I can reasonably look for some solutions to this equation and some x-intercepts. So I set my function equal to 0 to find my x-intercepts. I factor a negative 2x out as the common factor, and I get that x could be 0 or x could be negative 3. And my two solutions are going to be at 0 and negative 3, which also makes sense as they are the same distance from the axis of symmetry on both sides. Now, the y-intercept is where we run into a little bit of trouble, and that's where the c comes into play. You might remember that our y-intercept is always going to be at the value of c. But if there is no value of c, then we should anticipate our y-intercept would be at 0, 0, which is the point that we already got right there. We know that point already. We got that from solving for the x-intercept, so it ends up being a redundancy where I see the same point again. That will happen anytime c is equal to 0, because you're going to anticipate that that solution is going to be there, and both of the coordinates are then going to be 0, provided that there's a b term, which we'll talk about momentarily. But that leaves us with an interesting problem. We had always sort of graphed both sides, mirrored the image of the y-intercept over to the other side of the axis, and I don't have an extra point to image over to the other side. You always have the option of just determining any point that's on either side and mirroring that point. So for the sake of conversation, I'm going to use 1. So let's figure out what f of 1 is, just so we can have an extra point to mirror, because I lost my y-intercept that I would normally mirror. So that's negative 2 times 1 squared minus 6 times 1. Negative 2 times 1 squared is negative 2, negative 6, negative 6. That's negative 8. So I should anticipate a point at 1, negative 8, way down here. Because that point is 2.5 units away from the axis of symmetry, we should expect the other point, another point on the other side, also 2.5 units away from the axis of symmetry, and that would be at the point negative 4, 8. So our two x-intercepts satisfied our distance from the axis of symmetry being the same, and we're going to expect these points out here. Now, there might be some logic that says, oh, he just picked a random point. No, I picked the point that was easiest to evaluate. Don't confuse that. You pick a point to take the role of that y-intercept. Normally, we would map the y-intercept. I don't have an extra point to map with the y-intercept. I lost that because it's also an x-intercept. So my mirroring just came from somewhere else. And I draw my parabola down. I try to round off the edge as best as I can, round off near the vertex, and that's my sketch of the parabola. This last point could have been anywhere. I could have picked I could have picked x is equal to 6 or 10 or 12 if I wanted to. But I picked one because it was easy to evaluate and it was easy to mirror image on the other side. So that's the case specifically if c equals 0. So what if b equals 0? So let's take a look at 0.5x squared minus, I'm going to adjust this. We're going to change this to a 4. 0.5x squared minus 4. So here we have a is equal to 0.5. C is equal to negative 4. But now it's going to be b that equals 0. And that's going to have a much greater impact on some of the key characteristics of the graph. Right out of the gate, we try to figure out the axis of symmetry in the vertex, and we are stopped dead in our tracks. We have nowhere to go. Our axis of symmetry is just going to be the y-axis. Now, just figuring out that part doesn't necessarily guarantee that the axis or the vertex will be on the origin. I don't want you to think that those two things are synonymous. I can substitute 0 into my original function and get negative 4, which means my vertex needs to be at negative 4, at the point 0, negative 4. Again, I failed to mention a was positive. I know this bowl is going to open up. I'm comfortable writing those points down there so they're not in the way. So now we can try to solve and figure out our x-intercepts. This is a perfect candidate for the square root method. The missing linear term makes the square root method a very attractive option. We take our square roots, we're left with the square root of 8, which is also known as 2 root 2. And they are opposites of one another, which we would expect because we need them to be the same distance from the axis of symmetry. And they're approximately negative 2.8 and positive 2.8. So we'll go right about here, right about here. We want to see that mirror imaging, and that's what we have. Now, unfortunately, the presence of b being 0 makes the y-intercept also the vertex. It ends up making them the same. So if I was to go back and try to figure out the y-intercept, I would look at that c value and say, oh, my y-intercept is at 0 or negative 4. I already have that point. So that's not going to help me in terms of my graphing. So if you find yourself after these steps with only 3 points and no one to mirror image, then you have the responsibility of finding another point. Similar to what we did in this example, where we used 1 and then we mirror imaged it over, we need to do the same thing here. And for the sake of simplicity, I'm just going to use 1 again. You can use any number you want, but I'm just going to use 1 again. 1 squared is 1 times 0.5 minus 4 is negative 3.5. So I'm going to have a point at 1, negative 3.5. And then, of course, it's mirror image on the other side. And now I can reasonably draw my parabola to go through all of those points. So you saw here the role that C plays in helping us determine the y-intercept. If C is missing, then we should anticipate a point that's on the origin. Not necessarily the vertex. Well, clearly we did not get the vertex as being on the origin, but a point on the origin. Here we had b equals 0. That sticks our axis of symmetry directly on top of the y-axis. It doesn't allow us to move right and left. We found solutions that were opposites of each other, which is what we would expect if our axis of symmetry is on the y-axis. We need to be the same distance away from those. And then in both of those cases, because I was missing an input from the y-intercept or a contribution from the y-intercept, in this case, it was just a repeat of the vertex. In this case, it was a repeat of one of the x-intercepts. Because I got a repeat in the y-intercept, I have a need to find another point. So if I can find one more point, I can then mirror image that point to the other side, which then allows me to map it a little bit better. Could you draw a parabola that goes through the vertex and the two x-intercepts? Sure. But if we're doing this by hand and we're going through the trouble of doing this by hand, we want to try to make them as accurate as we possibly can. And kicking in that extra contribution from another point can make a difference.